Hi everyone and welcome back to NTE. In today's video what we're doing is we're really just giving ourselves a chance, right, to practice some electrochemistry, right. So what we're doing today is we're focusing on question 8 and question number 9, right, adopted from November 2015. Okay. We are also going to be using the standard reduction potentials table for A, right, which you can find at the back of your question paper. With that said, let's get started. Question number 8 says that learners are given the following two unknown half cells, right? So half cell 1 is made up of a species Q. Half cell 2, surprisingly enough, if you look at it, right, it's made up of an unknown species R, right, which has an anion, okay, as its reduced species. Okay. They further say that during an investigation, right, to identify the two half cells, the learners connect each half cell alternatively to a cadmium, right, half cell under standard conditions, right. For each combination of the two half cells, they write down the net cell reaction and measure the cell potential. Okay, so these are the results that the learners obtained. Okay. We see that for both of these combinations, right, either connecting the cadmium half cell to the half cell that contains species Q, or connecting the cadmium half cell to the species R. Right. I like to visualize these situations, so I'm just going to quickly draw sketches of these, right? And also another thing that we need to note is that for each of these combinations, the cell potential was positive, right? So then we know that our direction, okay, of electron flow in the external circuit is going to be from right to left. Okay. So just notice for half cell number 2, right? This is very similar to the She half cell, right? And it could have been the She half cell. It's just that we have an R minus here, okay, as a reduced species. So that is not going to qualify for the She half cell. Remember that the She half cell is a standard hydrogen half cell, and that's basically platinum, hydrogen gas, right, and H plus in solution. Okay, so this is something that basically functions in a similar way to the She half cell in terms of that it needs a platinum surface, right, for it to be able to actually have a surface area to be in contact with the electrons, right? But we don't know what it is for now, but we do know that it is something that acts like this She half cell, right, or uses the same setup. Okay, right, so we can use all of this information that has been given to us to fill in some labels in these two cells, right. Let's start with combination number 1, right? So combination number 1 is going to be this first sketch over here, right? And remember that I already noted the flow of the direction, sorry, of the electron flow due to the positive voltmeter reading, okay? So we know that the electrons are flowing in this direction, okay? That's the first thing we know, right? And now that we know that, we can now easily identify that the source of electrons, right, is from the anode, because that's where oxidation occurs, right, and they are moving to the cathode. Alright, so if we break this first net cell reaction into a oxidation, right, and a reduction half reaction, right. So for oxidation, right, we know that we are always going from something that is solid to something in solution, right? So our reactant for oxidation has to be a solid species, which is going to be this cadmium, right? So cadmium solid, right? That is being oxidized into cadmium 2 plus ions in solution. And obviously that's going to release 2 electrons. Right. Now let's go for the reduction half reaction. Well, reduction is always something in solution going into a solid, right? So that's going to be this unknown Q species, right? It's going to have to gain 2 electrons and then it becomes solid Q. Right, so now we can identify that the cathode, right, that is a solid Q, right, metal, and then at the anode we have cadmium, that's metal, right. So then this solution must be something that contains cadmium 2 plus ions, right, and as oxidation occurs, the cadmium metal is going to also go into solution as cadmium 2 plus ions, right. On the other hand, this solution over here has to be a solution containing Q2 plus ions, right, and they are basically going to move towards the cathode and be reduced on its surface, right. So that's it for combination number 1. We now know who is who. Okay. We can also add a little bit more of extra information over here, right? Because we know that the cadmium, right, is undergoing oxidation, right? We can now actually say that the cadmium is the reducing agent in this case, right? And it's actually the strong reducing agent. And then this Q species is going to be a strong oxidizing agent. Right. So let us put this to the side a little bit. Okay, so now let's analyze combination number 2. Right, so first things first, let's just put in the direction of electron flow over here. Right, so that's from right to left. Okay. And this is also confirmed when we look at the net cell reaction, right, because we can see that this species R, right, which is a gas, is actually undergoing reduction and becoming a anion, right? So we can write its half reaction as basically R2 gas, right, and it has to gain 2 electrons in order to become 2 R minus anions in solution. Okay, so those are present in here in the beaker, R minus. Okay, all right, and then on the other hand, okay, if you look at what's happening to the cadmium, right, it's doing exactly the same thing it was doing in the first combination, right. It's still undergoing oxidation because you have cadmium, solid going into cadmium 2 plus, right, and that's obviously going to release 2 electrons. Okay, right, so we have the same setup on this side. All right, so this, okay, is the anode, that's the cathode, right, and then also we can, let me just label this. This is solid cadmium, right. Remember that that piece right there is platinum, right. Okay, all right. So we can also say over here, right, because cadmium, right, is undergoing oxidation, it's the reducing agent, okay, and this gas R, right, is going to be the oxidizing agent. So now if we just quickly go back to these cell potentials, right, remember I said that the second combination is a much stronger cell, right, yeah, because it has a larger cell potential, right, so it's like having a 3-volt battery and a, what other volt battery do we have? Okay, it's basically like comparing a 3-volt battery with like a 30-volt battery, right? The 30-volt battery can supply much more energy, right, for a longer period of time, which means that it is stronger. Okay, so when we look at these two half cells, right, even though for both of them, right, because they are galvanic cells, right, these two species compared to each other are strong oxidizing and reducing agents, right, but like I try to illustrate here or to remind myself in a visual sense, right, for combination two is much greater, right. I'm going to use maths notation here. Okay, so the strength, right, of combination 2, okay, is greater than the strength of combination 1 over here. Right, so which means that, okay, obviously you can't compare cadmium to cadmium, right, but basically this R2 oxidizing agent is a stronger oxidizing agent than this oxidizing agent Q, right, whatever that is. Okay, so we are given the E0 cells for both of these combinations, so we can easily identify what is Q and what is R, right, just through calculation, and we'll do that soon. Okay. Right. Question 8.1 says to write down 3 conditions needed, right, for these cells to function as standard cells, right. So this is just theory, right. I'm not going to write it down. Basically, you should know by now that whenever we are dealing with these type of experiments and we are dealing with them, like they said over here, right, under standard conditions, right, it means that what we are doing is that we are evaluating these cell potentials, right, these standard E0 cells, right. We are evaluating those under the conditions whereby any concentrations, right, of our solutions, right, so any of these solutions in the beakers, right, always have to be at a concentration of 1 mole per decimeter cubed, right. The experiment itself has to be conducted in a environment or in a room, right, which is at a temperature of 25 degrees Celsius, right, that's room temperature. Okay, and then the pressure of any gases that we are using, right, that has to be a pressure of 1 atmosphere, right. So this R2 gas that we are putting into this first half cell over here, right, that has to be at a pressure of 1 atmosphere. Okay. Okay. Okay, so question 8.2, right, it says that for combination number 1, right, so we're now only focusing on combination number 1, identify the anode of the cell and Q using a calculation, right, so that is basically what we were talking about. Okay, so if we just go back, right, we already identified the anode of the cell, right, and that is the cadmium metal, right. Okay. Right, so they didn't specify here whether we need to use the formula or the name of this thing, so we can use either or, right? So you can just write CD, right? Or you could write it out in full. Okay. Right, so now let's go on to identifying what is Q, right, by means of a calculation. Okay. Okay, so in order to evaluate or to identify what is Q, right, we need to um, calculate its standard reduction potential, right. So we know that we're just going to be substituting into the equation, right. You can find this equation at the back of your test paper as well. E naught cell is equals to E naught cathode, right, minus E naught anode, right. And if you can remember, we already identified that the cadmium, right, is the species at the anode, right? So it's the one that's undergoing oxidation, right? But when we make this specific here, right, we don't really care about the fact that it's undergoing oxidation. We are more concerned about what is its standard reduction potential, right? So going from cadmium 2 plus to solid cadmium, right? So we just need to go to our standard reduction potential table, right? And I'm using table 4a just to get the value, right, for the standard reduction potential of cadmium, right? So let's just quickly go there. Oh, there it is, right? So cadmium 2 plus going to solid cadmium, right? That um, reduction half reaction, right? That has a standard reduction potential of minus 0.40. Okay, so we're just going to jot down that value. That's what we need. Okay, so that is going in over here in our calculation. So it was minus 0.40 volts. Okay, we can now substitute in E naught cell and then evaluate the standard reduction potential of Q2 plus to Q, and then we can go back to table 4a so that we can identify what is Q. Right, so then therefore this works out to be okay, we get minus 0.27. Okay, so now we have to just go back to the table and go hunting for this value. Right, we obviously know that it's going to be below the standard reduction potential of hydrogen because that's the one that has 0 volts. Yeah. Okay, so here we are back on this table again. So we're looking for minus, oh, there we go, minus 0.27. Okay, so this is actually a nickel cadmium light battery. Okay, so we can even confirm what we were talking about earlier on using our direction arrows, right? So if I just draw a mini version of it here, okay, remember this is going to identify who's the strong oxidizing agent and who is the strong reducing agent. Okay, we take this and put it on the diagram, right, or on the table, right, with that middle line going through these equilibrium symbols, right, you'll be able to see that, okay, nickel 2 plus, right, ions, those are strong oxidizing agents. Okay, and then the cadmium, right, just move this out the way a little bit. Right, and then the cadmium, right, is the strong reducing agent, right? So basically that is why the cadmium is at the anode, right, because it's going to undergo oxidation that way around, okay? And then the nickel 2 plus ions that are in solution, right, they are going to undergo reduction at the cathode and become solid nickel that way around. Okay. Okay, so identify Q by means of a calculation. We just did the calculation and Q is nickel. Okay, or you can use a symbol as well. Okay, so nickel. Question 8.3, right, we are now looking at combination number 2, right, and we are asked to write down the oxidation half reaction and also the name or formula of the metal used in the cathode component. Okay, that I feel we already have on our sketch. Okay, So we want to write down the oxidation half reaction. Well, that's just going to be writing the oxidation half reaction for cadmium over here, right? And then they want us to identify what is the metal used as the cathode. That is platinum. Okay. Alright, so for the oxidation half reaction, that is going to be cadmium. You can even put in the states if you want to. Going to cadmium 2 plus and releasing 2 electrons. Right, so that's that. And then over here, I'm going to use the formula. Right, so the metal that is used in the cathode component, like we said, that is platinum. Yeah. Question 8.4, right, it says arrange the following species in increasing oxidizing ability. Okay. Explain fully how you arrived at the answer. A calculation is not required. Okay. So we don't really need to, well, for me, this says that I don't need to show a calculation, but then if I need to do a calculation because I feel like I need to do a calculation to identify what is R, okay? Yeah, okay, so I already identified that Q is nickel, right? So then that is going to be the nickel 2 plus ions, okay? And we already saw that that was, what do they want us to compare here? Increasing oxidizing ability. So in other words, we want to arrange this from the weakest, from comparing these three, right? So we want to arrange this from the weakest oxidizing agent to the strongest oxidizing agent, right? So it's just a matter of going back to table 4a and just seeing who is at the bottom and who is at the top, right? Because remember, go on table 4a, right, as you move upwards, right, that's where you see increasing oxidizing ability. Okay, so I'm going to try to get table 4a completely on the screen for you, but I don't promise anything. Okay, but so far what we've done is that we've identified that Q is nickel, right? So we don't have to worry about that. I want to identify what is R. Okay, so I'm going to do a calculation for that as well, since I am given the cell potential, right, of combination 2. Okay, so we can quickly do that. Alright, so basically when you do this calculation, right, this works out to be a standard reduction potential of 1.36 volts, right? So notice that this is a side calculation, right? So this is not something that you would show, right, as part of your answer. You would just do this somewhere on your question paper or something like that, but don't include it in your answer script, okay? Right, so we're just going to use this value to go and identify what is species R, right, and that's going to be from table 4a, okay? Okay, so we're back on our table, right, and we're looking for 1.36. And there it is. Okay. Okay, so that is actually chlorine gas. That's quite nice. Okay. So if we just look at this situation, right, and we think of that little sketch that we drew, okay, the chlorine gas is obviously what's being fed into the system, okay, and then it gets reduced on that platinum piece of metal, and it becomes Cl minus ions in solution. Okay, so this is going in this direction, we already identified. Okay, which means that the chlorine okay, is a strong oxidizing agent. Okay. Okay, but remember with the question 8.4, right, what we're really trying to do is to organize all of these oxidizing agents, right, in order of increasing oxidizing ability. Okay, so I said I'm going to try and get this table completely on the screen. So let me try and do that. Okay, so here is table 4A on the screen, basically with all our identified reduction half reactions, right, circled, okay? And I know that you're seeing now, you're just seeing strong, strong, and you're like, okay, now everything is just strong, okay? It's strong compared to whatever you are comparing it to, okay? So what we're looking at here is always relative strength, okay? Right, so we identified that this chlorine gas is, ignore the strong for now, basically it's an oxidizing agent, okay? And also the nickel 2 plus, right, is an oxidizing agent, okay? Then if we go to the cadmium, right, reduction half reaction, okay? For that one, we identified that solid cadmium is a strong reducing agent, which means that on the other side, the cadmium 2 plus, right, is going to be a weak. Okay, this is a weak oxidizing agent. Okay, but now we want to arrange these. Okay, remember from the weakest oxidizing agent to the strongest. Okay, so you can remember this arrow over here, right? This is what we want to look at, increasing oxidizing ability. Okay, so you can already see, right, going upwards in this table. Okay, the species that is the highest up, okay, is the chlorine gas. So this is our strongest. If we put more of a descriptive word next to this chlorine gas, right? So this is our strongest oxidizing agent, okay? And then in the middle is going to be the nickel 2 plus, right? And the weakest oxidizing agent from these three is the cadmium 2 plus ions, okay? Okay, we identified that combination number 2, right, is a stronger cell than combination number 1, right? So then you can see that if you look at where you identified your oxidizing agents, okay, this gas R2, which we now know is chlorine gas, okay, the chlorine gas, okay, is a stronger oxidizing agent than okay, and in fact over here we just put our label in the incorrect place, right? It's more correct to say that the chlorine gas is a stronger oxidizing agent than the nickel 2 plus ions, right? Since they are the ones undergoing reduction. Okay. Right. So then after that, you can see that you would still need the table really to check for the relative strength between these two oxidizing agents and the cadmium 2 plus ions. Okay. Right, so then to finalize this answer, right, remember that we were really trying to arrange over here. Okay, so what we have as the first statement here is a comparison of their strengths. Okay, so then to arrange them, you can then finalize and say, therefore, the order of increasing oxidizing ability okay, that is going to be, remember, we want to go from the weakest to the strongest, so then it's going to be cadmium 2 plus, then the nickel 2 plus, and then lastly Cl2. Right, so moving on to question 9 of this paper. Okay, We have over here again a simplified diagram which represents an electrochemical cell used for the purification of copper. Right, so for this one they're telling us exactly what we're looking at over here. Okay, alright, so you can see there's a DC source, right? Electrode A, electrode B is the impure copper, right? And then you've got some electrolyte. Okay. Alright, so um, they've omitted for us over here the symbols of a battery, okay? But you should know from the theory, right, that whenever we are trying to purify copper, right, we always place the impure copper at the anode, right, so that it can undergo oxidation, right? In other words, so that any solid copper that is in here, right, together with all the other funny metals that it's with, okay, it can go into solution, right? In other words, undergo oxidation and become copper 2 plus, right? This is already going to be a copper 2 plus solution. Okay, so something like copper sulfate. Let's put another one there. Okay, so basically there is already some copper 2 plus ions in solution, right? And then for each copper 2 plus ion that is deposited into solution, right, one that is already in solution, okay, will then go and deposit itself, right, or be reduced on the anode A, right, which is going to have to be the cathode, since you want a reduction to happen over there. Okay, and then this is that whole theory about this cathode, right, basically increasing in mass, because as the copper keeps depositing, right, you get a layer of copper, pure copper, being plated on this electrode. Okay, right. So we can now move on to the questions, right? So question 9.1 is theory, right? Define the term electrolysis, right? So we all know that electrolysis, right, is an electrochemical process that we use, right, to drive non-spontaneous reactions, okay? Or you can say that electrolysis, right, is the electrochemical process that converts, right, electrical energy to chemical energy, okay? 9.2, right, it says give a reason why a direct current source is used in this experiment. Well, the reason why we use direct current is so that electron flow, right, is always in one direction as well. Okay, so yeah, let's just write that down. Okay, so this is to ensure letter E, a single direction of electron flow. Okay, otherwise we are not going to get anywhere, because then if we use AC, then it's going to flip around. Okay, 1 minute this side is going to be the anode, and then the next minute the same side then becomes the cathode, right? So then it reverses what we've been doing. Okay, so it's just going to keep flipping back and forth, which means that you're not actually doing anything. So that's why we need a DC source. Okay. Right, so question 9.3 says write down the half reaction that takes place at electrode A. Right, so that is the reduction half reaction. Okay, so reduction half reaction. Okay, that's the copper 2 plus ions that are in solution. Okay, they gain 2 electrons at the cathode surface and they become solid copper. Okay. Question 9.4, right, it says due to small amounts of zinc impurities in the impure copper, the electrolyte becomes contaminated with zinc 2 plus ions. Okay. Refer to the attached table of standard reduction potentials to explain why zinc 2 plus ions will not influence the purity of copper obtained during this process. Okay, so basically what they're saying is that some of the zinc 2 plus ions, okay, from electrode B are going into solution, okay, like that. Right, so they are also being oxidized. Okay, so now we need to go back to our table to explain why the presence of these zinc 2 plus ions, okay, in solution, okay, why they won't affect the purity of copper that we will get over there. Right, so in other words, what they're trying to say is that this zinc 2 plus ion, okay, doesn't actually undergo reduction. Okay, so if it doesn't undergo reduction, it means that the zinc 2 plus ion has to be a weaker oxidizing agent compared to the copper 2 plus ions. Okay, and that's just something we're going to need to compare, sorry, not compare, confirm, right, on this table of standard reduction potentials. Okay, so the only thing we want to confirm is that the zinc 2 plus ions, right, are weaker oxidizing agents compared to the copper 2 plus ions. Okay. Okay, so here's our table, right? And basically now we're just searching for the reduction half reaction of copper and the reduction half reaction of zinc. Okay, so just be careful with the copper because there's a lot of them, right? So you can see the copper plus, copper 2 plus with one electron. What we're looking for is this one, copper 2 plus gaining 2 electrons. Okay, and then we need the zinc. Okay, so there's the zinc. Right, if you also notice what just happened on the screen, right, I had to move downwards, okay, in order to get to zinc, right? So that is basically telling me that the zinc 2 plus ions, right, I can already tell that those are weaker oxidizing agents because I know that going up this table is showing me increasing oxidizing ability, right? So you could get to that conclusion that way, or you could use my direction arrows. Okay, that's the one component that you want to compare. You want to compare that with the zinc 2 plus ions, right? Okay, so if I zoom out a little bit on this so that you can just see the relative position of these two reduction half reactions, okay, if you wanted to use the direction arrows, okay, remember that the direction arrows are basically helping you to figure out, right, when comparing two reactions, okay, so you're just figuring out between these two reactions that you're comparing who is the stronger oxidizing agent and who is the stronger reducing agent. Okay, so from this, the direction arrow would tell you that, well, comparing these two, the stronger oxidizing agent is the copper 2 plus ions. Okay, they are the stronger oxidizing agent. So then it will make this the weaker oxidizing agent. Okay, and that makes sense because the direction arrow is telling you that zinc metal is the stronger reducing agent. Okay, so yeah, that's basically why the zinc 2 plus, right, going into solution doesn't really affect the purity of the copper that we obtain because it doesn't undergo reduction. Okay. Okay, so I would like to add something here. I'm just thinking now. Right, so thus copper 2 plus ions are, I'd like to add this word selectively, okay, reduced at the anode, right? So it's like a competition, right, between the two ions, and the copper 2 plus ions win, right? So then therefore the copper that we obtain is still pure. Okay. Right, last question on this paper. Right, question 9.5. It says after the purification of impure copper was completed, it was found that 2.85 times 10 to the minus 2 moles of copper were formed. Okay, right, so that's the moles of copper that were formed on the cathode. Right, so let's just go back. Okay, so that's basically referring to this reduction half reaction. Okay, so the number of moles of solid copper that were formed at electrode A is this. Okay, the initial mass, right, of copper B, right, which was the impure copper, was 20 grams. Right, calculate the percentage of copper that was initially present in electrode B. Interesting question. Okay. Okay, so let's just make sense of what is happening over here, right? They want us to calculate the percentage, right? In other words, percentage. Think about it. It's the amount, right, of copper that was initially in electrode B. Okay, let's look at a picture so that we can see this more clearly. Okay, so there's electrode B, right? Like I said in the beginning, there's some copper, right, in this impure electrode. Okay, so they are telling us that when this whole process is complete, right, all of this copper will come out, okay, because it's complete, right? So they're basically telling us that this reaction has run to completion, right? So all of the copper that was initially present in that impure electrode, right, all of it is now deposited on electrode A, which is what we wanted, okay? We wanted to extract that copper from the impure ore, if you want to say it like that. Okay, so now they're telling us the number of moles, okay, that were obtained from this process. Okay, so now you can see where this is going. Okay, it's now going to go into stoichiometry, right? Since we know the number of moles that were obtained, okay, we can easily convert that to the mass that was obtained, right? We just need the molar mass of copper, right? Which means that we need our periodic table. Okay, so then once we have the mass of copper that was obtained, right, then we can just divide it by this total mass, which is basically the initial mass of the electrode. Okay, so we can even write here that the total mass, okay, equals 2.0 grams, right? So then the percentage, okay, of copper that was initially in there is going to be the mass of copper, right, that we took out, divided by the total mass. Okay, times by 100, because we want a percentage. Okay, so we've now developed for ourselves a little equation that we're going to use. Okay, we just now need the molar mass of copper, right? Because we want to substitute it into the formula, number of moles is equals to mass divided by molar mass. We're going to rearrange this. Okay, no. Remember that for our exams, right, you always need to show substitution first before you start rearranging. Okay. Okay, so let's go to a periodic table and just find the molar mass of copper, right? Okay, so here's your periodic table, and look at that. Copper is actually used as like the key of this periodic table. So it has a molar mass of 63.5 grams per mole, right? If you wanted to find copper on the table itself, it's right over here. Okay. Okay, so going back to our calculation over here, from the periodic table, we got this as 63.5 grams per mole. Right, so substituting in the number of moles that were given to us, 2.85 times 10 to the minus 2. Okay, we want the mass, and we just found the molar mass. Okay, so then therefore the mass of copper that was originally Can even write it like that. Mass of copper, right, that was sort of like embedded in that impure ore, right. Right, so that works out to be 1.80. Okay, so we need to round off to 2 decimal places, so this is going to be 1.81 grams. Okay, so 1.81 grams of copper was in that impure ore. We take that, we substitute it here, 1.81 divided by the total mass of 2.0 times that by 100. Okay. Right, so on the calculator itself, we can still use the complete answer just to keep accuracy, right? So we know that we need to take this answer and divide it by 2.0. Okay, and then we need to times that by 100 to get the percentage. Oopsie. Okay. So again, rounding off to 2 decimal places, we get 90.45%. Okay. So 90.45%. Right, so that was actually quite a significant amount of copper, right, in that impure ore. Right. So yeah, that's it for today's video, matriculants. I hope you guys learned something, and I will see you next time.